All right, so today we're going to look at some basic introduction to hyperbolic trig functions. Hyperbolic trig functions are one of those things that is kind of hit and miss in the coverage in college algebra courses and in calculus courses. And then sometimes it pops up sort of mysteriously in differential equations, depending on who your instructor is. That was how I got introduced to hyperbolic trig functions. Nobody ever talked about them until all of a sudden I had a professor who was just in love with them. So the purpose of this discussion is simply to introduce the basic idea, talk about some of the definitions, and sort of give you some guidance in terms of the general overview. Most of these hyperbolic trig functions are covered in, if not college algebra textbooks, they are covered in calculus textbooks for sure, but they're usually kind of off the beaten path. They're sort of hit and miss in terms of whether professors cover them or not, whether they're even on the syllabus. But you can usually find them if you go to the index or the table of contents and you look for them specifically. Sometimes they're sort of left off. That are put off to the end of another chapter, maybe that gets skipped over, or is at the end of a chapter that gets covered, but then you just don't cover that last section. So usually it's out there kind of milling around. You have resources available to you, but you have to go out of your way in some cases to find them. And so I just want to give a brief discussion of sort of the definitions, general properties, in case you encounter them, or in case you just want, like, what is this sinh? What is this sine h thing? Is this sine of h of t? No, it's not that. Okay, so hyperbolic trig functions, they are similar to, but different from regular trig functions. So regular trig functions are based on the idea of a circle, and hyperbolic trig functions have relationships based on the idea of a hyperbola. And so the hyperbolic sine and cosine functions are actually defined also similarly to regular circular, triangular sine and cosine functions. But in terms of exponentials, regular trig functions are defined in terms of complex exponentials, essentially Euler's formula, which is, again, something that you may not have run into in calculus. Maybe you ran into it if you dealt with complex exponentials in a pre-calculus course, but which really are sort of central to differential equations. So regular sine and cosine are defined in terms of complex exponentials like this. So hyperbolic cosine is defined in terms of e to the it plus e to the minus it all over 2, based on Euler's formula. If you have e to the ix, that's cosine x plus I sine x. If you replace x with minus x, then that changes this sign because the minus can come out. And then cosine of minus x is still cosine x because it's an even function. And then you add those two together, you get cosine can be defined this way. And then the sine function is derived basically the same way, except that you subtract the two versions, e to the ix and e to the minus ix. And when you solve for sine, you get this expression, e to the it minus e to the it all over 2I. Now, one of the nice things about this definition is that you can see why there's a 4-cycle pattern. When you take the derivatives, why does it go from sine to cosine to minus sine to minus cosine? It's because of those powers of I that are coming out every time you take derivatives. So that's useful in terms of like understanding the behavior and the patterning. And of course, as you know, you may recall from dealing with complex exponentials, if you've run into them before, they basically describe like the rotation of a circle, right, around the origin in the complex plane. So there's a lot of reasons, particularly in differential equations, but certainly generally why these definitions for sine and cosine are really powerful. But in hyperbolic trig functions, the definitions are essentially the same, except there's no complex components. So hyperbolic sine is just e to the t minus e to the minus t. So same thing here, divided by 2 as opposed to 2i. And then hyperbolic cosine is e to the t plus e to the minus t, again, similar here, divided by 2. So these are basically the same, defined in exactly the same way. The minus signs are the same, the exponentials are the same. The only thing that differs is that hyperbolic trig functions are real functions based on real exponentials, and sine and cosine, well, they have this real outcome that you can derive these in many different ways. Their building blocks in exponential form are complex exponentials. And that's what gives them that periodic behavior. Now, the really nice thing about these definitions also is that we can see a lot of properties from regular trig functions are mirrored in some respects in hyperbolic trig functions. So hyperbolic sine of 0 is also 0, just like sine of 0 is 0. And similarly, cosine of 0 is 1, and hyperbolic cosine of 0 is also 1. So it can be really helpful to kind of understand these similarities, even if you don't necessarily completely follow the complex exponential definition, but to recognize that there's a lot of similarities here. And so you can use your knowledge of the regular trig functions to help you with the remembering the hyperbolic trig functions. There's just a couple of places where the graphs are, or the properties are different, and we'll go through those. But sine and hyperbolic sine are both odd functions. Cosine and hyperbolic cosine are both even functions. So again, these properties are really similar to each other. Now, the same thing applies, of course, to the other hyperbolic trig functions, which we'll define in a moment. But they're defined very similarly. The even and odd properties are the same, and their behavior at 0 is typically also identical. So regular sine, we see this periodic behavior. Hyperbolic sine is not periodic because hyperbolas are not periodic. Cosine, again, periodic behavior. Hyperbolic cosine, not periodic, but you can see this is an odd function. It goes through the origin with the first quadrant looking like the third quadrant. Same thing here. Hyperbolic cosine, even function, also an even function. Now, the other 4 hyperbolic trig functions are defined basically the same way their regular trig functions, the circular trig functions, are defined. So tangent, hyperbolic tangent is defined as hyperbolic sine over hyperbolic cosine. And if you simplify that, you get, again, it's a definition in terms entirely of real exponentials. Cotangent is defined as cosine over sine. So hyperbolic cotangent is hyperbolic cosine over hyperbolic sine. And again, it's just the reciprocal of tangent. Secant is 1 over cosine. And so hyperbolic secant is also 1 over hyperbolic cosine. Again, just reciprocal. And cosecant is 1 over sine. And so hyperbolic cosecant is 1 over hyperbolic sine. And again, it's just reciprocal. Now, because the number of syllables in hyperbolic cosecant, for instance, or hyperbolic cotangent, these are all very long expressions, and math people are fundamentally lazy. We like our shorthands. So we have shortened the names for these. So instead of hyperbolic sine, we usually say sinh. Instead of hyperbolic cosine, we usually say cosh. Instead of hyperbolic tangent, we often say tanch. Cotanch, hyperbolic cotangent, cotanch. Hyperbolic secant is sich. If you are familiar with Dune, it's the same word for the desert dwellings of the Fremen, it's sich. And then hyperbolic cosecant is cosech. And then these are the graphs of our 4 other trig functions, again, just for comparison. Regular tangent, circular tangent, again, periodic behavior, hyperbolic tangent, not periodic behavior, but you can see they both are odd symmetry and they both go through the origin. So hyperbolic tangent of 0 is 0. Cotangent, undefined at 0 in both cases. Hyperbolic secant versus regular secant. So secant is even symmetry because cosine is even symmetry. Also even symmetry. And again, hyperbolic secant of 0 is 1, just like hyperbolic cosine of 0 is 1. Same thing for hyperbolic secant. And then for cosecant, again, we have the odd symmetry and undefined at 0 because sine, hyperbolic sine or regular sine are both 0 at 0. Now, the identities that you use for all of these are also very similar, but the difference is that they're fundamentally in the hyperbolic world based on hyperbolas and not on circles. So if we think about the circle being x squared plus y squared equals 1 for the radius of the unit circle, then x and y are both examples of basically the trig functions, right, on the unit circle. X is cosine, y is sine. And if you construct that x squared plus y squared equals 1, you get your unit circle. And that is the standard Pythagorean identity. The corresponding identity in hyperbolic world is x squared minus y squared equals 1. So hyperbolic cosine squared minus hyperbolic sine squared equals 1. So that's the main difference. And all the other differences in all of these other identities are all derived from the same thing. If you divide your original identity by cosine squared, you end up with 1 plus tangent squared equals secant squared. And if you do the same thing, you divide cosine squared, and then you in this identity, they're typically moved around to account for the minus sign. But you end up with 1 is equal to hyperbolic tangent plus hyperbolic secant. Again, because they move the secant squared divided by cosine squared, or sine squared over cosine squared over to the other side of the equation. Again, same thing here. If you divide the original identity by sine squared, you get sine squared over sine squared is 1, cosine squared over cosine squared is cotangent, and 1 over sine squared is cosecant. You get this other identity. And again, this one is derived from the same thing up here, but again, slightly rearranged and divided around. And again, similarly, you have sine squared identities. In the regular world, regular trig world, it's 1 minus cosine 2x times a half. Same thing, but there's an extra minus sign. Cosine squared, again, same basic identity. This, all you really have to worry about in terms of flipping between the two systems is where the minus signs go. And sometimes they're identical. Sine of 2x is equal to 2 sine x cosine x, and hyperbolic sine of 2x is 2 sinh cosh. Again, same identities. Now, typically, you don't really have to remember all of these. You don't use them often. Certainly, you don't see nearly as many problems, as, even when your professors cover them. I know even when I cover them, I don't necessarily expect students to remember as many of the identities for hyperbolic trig functions as I do for regular trig functions, because we spend a lot more time with these. They have a lot of uses that we can put them to. The main one to kind of remember is just this basic, you can call it the Pythagorean identity, but the relationship between cosine squared and sine squared, cosh squared minus sinh squared equals 1. And generally, if you can do that, you can, that's the one that comes up the most often. If your professor goes into spends a lot of time with these, which again is somewhat uncommon, then you can worry about maybe some of these other ones. Now, when it comes to calculus, the derivatives are almost all completely the same. The only thing that you really have to worry about is where the minus signs go. The derivative of sine is cosine in the regular trig world, and the derivative of hyperbolic sine or sinh is cosh. One of the minus sign differences is going to occur when you take the derivative of cosine. In the regular trig world, you get minus sign. In the hyperbolic trig world, you get positive hyperbolic sine. And then the other place you get a difference is actually in the secant derivative. In the regular trig world, you get secant tangent, but in the hyperbolic trig world, you get minus hyperbolic secant hyperbolic tangent, or sech tang. But the signs on all of the other ones and the form of the derivatives is all entirely identical, other than those two minus signs. So I think it makes them easy to remember. And if you're still, again, if you're still dealing with Calc 1, that's about as far as you need to go. But if you've done Calc 2, you may have encountered Taylor series. And again, the Taylor series for the two are very, very similar. The main difference is that the hyperbolic sine doesn't have this -1 to the n. So the formulas for both of these functions, same thing for hyperbolic cosine, the formulas for these functions are basically the same. The only difference is the regular sine alternates signs. So it's odd terms, x cubed over 3 factorial, x to the 5th over 5 factorial, so on and so forth. But the signs are alternating, plus, minus, plus, minus. In the hyperbolic trig world, these signs don't alternate. So it's x plus x cubed over 3 plus x cubed, x to the 5th over 5 factorial. So x cubed over 3 factorial plus x to the 5th over 5 factorial plus x to the 7th over 7 factorial. It's all pluses. Same thing for the cosines. So these are all even terms. 1 x squared over 2 factorial, x to the 4th over 4 factorial, but the signs alternate. So 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. But in the hyperbolic cosine function, the Taylor series is the same, but it's all pluses. And it's very easy to prove these. As an example, you can show that the derivative of the hyperbolic sine, if you just go to the definition, you can just take the definition of the component terms, pull out the half. The derivative of e to the x minus e to the minus x is going to be e to the x, and then you bring down the minus sign, which makes that a plus sign, plus e to the minus x, which is just a rewrite of hyperbolic cosine. Same thing if you take the derivative of hyperbolic cosine, the minus will come down and will make what started out as a plus here into a minus, but nothing else. So this term doesn't change, which means you can't pull a minus sign out of it. So it just turns into regular sine, hyperbolic sine. And then I've also included here just an example of using the Taylor series. You can derive this formula for the hyperbolic sine function using the definition. So the definition of e to the x in Taylor series is given here. And the definition of e to the minus x, again, is given here. And if you subtract these expressions for hyperbolic sine, what you get is that the ones will cancel, but the x's will add. And then the x squares will cancel, but the x cubes will add, and so forth. And then you divide out by the 2 to get the hyperbolic sine function. And so you can derive this hyperbolic sine formula very directly without having to, just from the definition, without having to take your traditional repeated derivatives and things like that. And then the last example I just wanted to mention here was, again, this typically where you encounter hyperbolic trig functions is in differential equations. And one way to establish a solution set for a differential equation is that it really has to satisfy two conditions. The solution sets have to satisfy the differential equation. So if I take the second derivative and I subtract the original function, I need to have them cancel out. Exponential functions will work as a solution set for this differential equation, but also hyperbolic trig functions will work. And typically, in addition to satisfying that differential equation, we also need to make sure that they satisfy a condition based on the Wronskian, that the Wronskian, when you do the calculation, that they don't give you a zero. And if you do the calculations for the first solution set with based on the exponentials, you get a constant, which is definitely not zero. And similarly, if you do the same calculation for the Wronskian based on the hyperbolic trig functions, you also get a constant, but that's not important, which is also never equal to zero. So if you haven't gotten to differential equations, don't worry about this. It'll come up. But if you have, then you can see that these are both going to satisfy the differential equation, but they are also going to satisfy our condition about independence. And typically, this is the context in which hyperbolic trig functions will come up in differential equations, is as some professors will, and I have had professors who do this, they just were like, I want to be super simple. Everybody's learned exponentials. We'll stick to that. We'll do our solutions based on those things. And then you have these other professors who are like, no. I really like my hyperbolic trig functions. And so I'm going to stick with these. And so this is actually where I first learned hyperbolic trig functions, when I had never heard of them before. So this is sort of our crash course in hyperbolic trig functions. Again, I think that the relationship between the hyperbolics and the regular sine functions are really fascinating. The exponential definitions versus the complex exponential definitions, but that's why I'm a math major.